Alright guys, in this video I am going to talk a bit about surface integrals and the divergence theorem. The good news is, basically, if I could summarize this chapter in one short sentence, it would be that we're going to calculate the flow across surfaces. We are not doing anything with flow along, only flow across. So if you have, basically, the best thing to picture is an open surface and a vector field, and you want to find the net flow of that vector field across that closed surface. It doesn't have to be closed, but that's the easiest scenario to picture. I am going to break up this slideshow into two separate videos. The first half will be just about flow across a surface when you have a vector field. In the second video, I'm going to talk about surface area. So what I like about this chapter is it really just builds upon information that you guys have already pretty much mastered. You already know how to find the net flow of a vector field across a closed curve. You have your path integral technique for doing that, the path integral of fields dot normal. And you also, and we have different notations for indicating that, but they all mean the same thing. And then when it is appropriate to use the Gauss-Green formula, if you've got a closed curve, and when you have no singularities inside your region, you could of course do a double integral over the interior of that curve using the Gauss-Green formula with the divergence. And good news, it's the same thing in this chapter. This is just another slide from a previous chapter. We are not going to be discussing flow along in this chapter. We kind of break things up into two separate chapters. Lesson 12 is about flow across. Lesson 13 is about flow along. So we're not really packing in quite as much material as we have in previous chapters. Our focus is simply on flow across, and you don't really have to worry about any of this flow along stuff you learned for at least a couple weeks. Again, we're not going to use the rotation of the vector field this chapter, since we're just talking about divergence, sources and sinks, flow across. So let's get to the new stuff. So what we really want is a three-dimensional analog of the Gauss-Green theorem. That's basically the big idea here. We want to have options for two different ways to compute flow across. And the good news is that the idea of divergence really extends pretty easily to three-dimensional space. And like I mentioned before, don't worry about flow along. All right, so let's get to the good stuff. So let's suppose that R is a solid region in 3 dimensions. Suppose that it has some boundary surface, C, that doesn't have any singularities on its interior. Or at least on the interior of that surface, we don't have any singularities in our vector field. Then the net flow of our vector field across our closed surface is measured by, we've got two choices here. We could either do a surface integral of field.normal over the outer skin of that region, or we could do a triple integral of the divergence over the interior of that region. Hey, guess what? That looks exactly like the Gauss-Green theorem. All I've done is I've gone in and thrown in an extra integral symbol, right? Does this notation look scary here with two integral symbols and then a loop-de-loop around it? Sure, but this notation is basically just taking a path integral and throwing in an extra integral symbol, and now it's called a surface integral. Similarly here, previously with the Gauss-Green theorem, we would double integrate the divergence, but in this case, since we're in three-dimensional space now, we are going to triple integrate the divergence. So basically, take the Gauss-Green theorem, add an extra integral symbol to both sides, and essentially that's what we're doing. Now, we do have to update the definition of divergence, and in this case, our vector field gets an extra component, a p of xyz, and our divergence of our vector field depends on another variable, z, and so divergence of the vector field is now dm dx plus dn dy, which you're familiar with, plus dp dz. All right, well, not really that big of a deal, right? We've moved up a dimension, so we've added one extra term. And that's all we really have to worry about there. By the way, a lot of you guys are going to go on to take this course or similar courses at another university that aren't going to use this net math notation that you're used to. And when that happens, you might want to be used to some of that terminology and some of that notation. So this slide is dedicated just to those of you who take further physics, engineering, math courses that don't use the same terminology as this net math course. So first of all, flow across, more commonly referred to as flux. And then we could update our notation here. So instead of saying field dot outer unit normal, I could just do capital F dot n. It means the same thing. It's just kind of a shorthand notation here. And then on the right-hand side, you don't really see quote-unquote div field in any other courses. This term is nice when you're coding in Mathematica because it's easy to type out, this string of letters, but it would be difficult in Mathematica to type out, del.f. So that would be kind of a pain to try to type in a computer. Honestly, when you're doing things by hand and on paper, this del.f notation is convenient because it's faster to write del.f than it is to write the divergence of the vector field. And just remember that you are already familiar with del. Del is a differential operator, actually a three-dimensional vector with three differential operators in it, ddx, ddy, ddz. And so the reason that it's okay to say that the divergence of the vector field is del.f is when we go ahead and take this dot product between del and our vector field m, n, p, we get dm dx plus dn dy plus dp dz, as you might expect. And like I said, n could just be a shorthand for outer unit normal. Now in the U of I net math notation, the reason I like this outer unit normal idea is it does remind you that in order for this formula to work the way that we expect it to, we want to look at the dot product between our field vectors and outer unit normal vectors here. So we want to make sure that these normal vectors for our closed surface are pointing from inside to outside. And then what we're going to do is we're going to look at the field vectors compared to those normal vectors, right? We look at that comparison between our field vectors and our normal vectors. That's done by taking that dot product, and if you accumulate all of those little with and against pushes, that's how our surface integral is going to give us the net flow of our vector field across our closed curve. Now, you guys had a pretty big bag of tricks from previous chapters with computing flow across. All of those tricks are going to carry over into this chapter. It's going to go from being a shortcut using closed curves to a shortcut using closed surfaces. So we had these questions where it said, is the net flow of the vector field across the curve from inside to outside or outside to inside? Well, the question is specifically vague, and it doesn't say that you need a precise numerical result. It's just inside to outside or outside to inside. And so depending on the nature of your vector field and the divergence of that vector field, sometimes there's a little workaround. Like for this problem, the divergence of our vector field was always equal to a positive number. And so when we invoked the Gauss-Green theorem to go from a path integral to a double integral of the divergence, well, that was the double integral of a number that's always positive, which means that our overall result was always positive. And so we were able to conclude fairly easily that the net flow of the vector field across our closed curve was inside to outside, really no matter the shape of our curve. It could have been this teardrop shape, it could have been anything else. We were going to get the same result. Well, good news, we have the same exact shortcut in this chapter. So in this case, I've got a fairly terrible looking vector field. Look at how complicated this three-dimensional vector is. I've got x's and y's and z's all over the place. It looks pretty terrible. So it looks like this will be a challenging problem. And then the surface also looks like it might have a very difficult parameterization. And so the question is the net flow of the vector field across the surface from inside to outside or outside to inside. That question sounds like it'll be difficult to answer. Good news, when you go ahead and compute the divergence of this vector field, when you take these three partial derivatives and add them together, honestly not much really sticks around in the end. We just have negative 3y squared minus 4, which is always negative for all values of x, y, and z. And so we get the same shortcut that you guys have seen before. Now we are going to invoke, it's no longer the Gauss-Green theorem, it's the divergence theorem. So this is the big theorem from this chapter. It's called the divergence theorem. And all it is a three-dimensional analog of the Gauss-Green theorem. Struggling to ink right there and talk at the same time, sorry about that. But in any case, what do we have? We have a correspondence here, inequality between a surface integral and a triple integral. Basically, we have two ways of doing our computation in this case. We can either do a surface integral over the boundary, or we can do a triple integral over the interior, and because we don't have any singularities to worry about, we can pick either one. Now in this case, what we want to do is we want to use the divergence theorem to get from our surface integral over to a triple integral where we can plug in this expression, negative 3y squared minus 4 for the divergence. And if we are triple integrating something that is always negative, we know that triple integral is going to give us a negative answer. So for any closed surface, not just the one they gave us in this problem, but for any closed surface that we could put in our vector field, the net flow of that vector field across that surface is going to be from outside to inside, a negative answer. These start to get a little repetitive once you've seen it once. The shortcut is pretty much the same every time. So you could change up your vector field if you want. You could change up your surface if you want, but the overall recipe is going to be the same. So we're going to compute the divergence of this vector field, dm dx plus dn dy plus dp dz. And in this case, we end up getting 0. You can kind of see, if you look closely here, you could see how I kind of finagled things to work out that way. The x component of our vector field has no x's in it. The y component of our vector field has no y's in it. The z component of our vector field has no z's in it. And that's good because then when we take each of these three partial derivatives, since each of those variables is missing one by one, each of those partial derivatives is 0, and 0 plus 0 plus 0 is going to give us 0. But the rest of the shortcut is the same. Again, we invoke the divergence theorem. So we say that this surface integral is equal to the triple integral of the divergence here. We're allowed to do that because A, we have a closed surface, and B, we have no singularities on the interior. Actually, we have no singularities at all, but we have no singularities on the interior of our surface. And so then we could throw in a 0 for the divergence of the vector field, and the triple integral of 0, of course, is always 0. So for any closed surface, the net flow of the vector field across that surface is 0. These are great little shortcuts. You see them come up on triad problems. You see them come up on the literacy sheet. You shouldn't be surprised if you were to see them on a quiz or a final exam. And what's nice is you've done this before. It's just now we have the divergence theorem instead of the Gauss-Green theorem. And they're basically, in spirit, the same idea. This slide, you guys have seen this before as well. I actually literally went into my lecture notes from a couple chapters ago and found this slide, and I just updated it for three-dimensional space. So let's see what's going on here. If the divergence of the vector field is greater than 0 for all points inside of your surface, then we know all these points are sources, first of all. And so the net flow of the vector field across that surface is from inside to outside. So I basically just went in and added an extra variable. And I changed the word curve to a surface. Those were really the only changes on this slide. So you guys have seen this before. It's nice when you get to use prior knowledge to learn something new. So you guys can just rely on that prior knowledge that you've worked so hard to learn. Similar idea, if the divergence of the vector field is negative, then all those points are sinks. And then the net flow of the vector field across that surface is from outside to inside. I know this still says C here. C is a surface, not a curve this time And then finally, we just saw this happen on the previous example. If the divergence of your vector field is 0 for all the points inside of your surface, then the net flow of the vector field across your surface is 0. We also had some just straightforward calculations in some previous chapters. We're going to do the same thing here. The key word you want to look out for is measure. If you see that we are asked for a measurement, we don't necessarily have the shortcut of just saying inside to outside or outside to inside. We actually do need to compute an integral. But if we are told to measure, and our region is, at least in two-dimensional space, if our region is rectangular, that's a good indicator that you don't really want to do a path integral. I don't really want to add a path integral for each of the four sides of our rectangle. I think that sounds painful. If you were going to do a path integral over the around the exterior of this curve, you would have to do a path integral for each of the four sides of the rectangle. That's terrible. You don't want to do that. Instead, a rectangle lends itself to doing a double integral over the interior. Look at these limits of integration. Nice little integers in this case. So that's an easy double integral to compute. We've got the same trick in this chapter. Instead of having a rectangle, we'll have something like a rectangular prism, but it's the same exact idea. So you don't even necessarily have to draw it. You can just describe it. So let C be the rectangular prism bounded by x goes from -1 to 4, y goes from -2 to 3, z goes from 0 to 5. Those are going to be your limits of integration for dx, dy, and dz. We do have a vector field that's given to us in this problem as well. We're going to want to compute the divergence of that vector field. That gives us a scalar that we're able to integrate in our triple integral. So we're going to use this divergence. Now, look very closely at this equation. You could see that the divergence of this vector field 5 plus 4x, it's not always positive or always negative everywhere in space. And so when you see something like that, the fact that it's not always positive for all values of x, y, and z, or always negative for all values of x, y, and z, that's a good indicator that you're probably not going to be doing that shortcut of just getting inside to outside or outside to inside. That's a good indicator that this problem is probably more appropriate for a measurement. Anyway, when you're doing these problems, you do want to actually invoke the divergence theorem. You want to make sure that you are explaining to your reader that you are allowed to move to a triple integral. You're always allowed to do a surface integral. You are always allowed to do a surface integral, but a triple integral is only allowed if you've met certain conditions. And the certain conditions you have to meet is, first of all, you need a closed surface. In this case, we have one, a rectangular prism. And then you need to make sure you're careful about singularities. There are absolutely no singularities to worry about in this problem. So we can easily invoke the divergence theorem. When you guys are doing these by hand, I really want to see this progression. I want to see this work here. Anyway, we know our integrand becomes 5 plus 4x. We know our limits of integration because we already got those for free in our setup. And I don't know if you guys really want to watch me computing this triple integral because it's not very exciting. So I'm going to go straight to an answer of 1375. And I would just encourage you guys on your own to go ahead and do that triple integral for practice and just to verify that answer. Now, we never stop at a numerical answer in these problems. You always write a sentence summarizing what's going on here. So because this is a positive result, the net flow of the vector field across our closed surface is from inside to outside. We care about this value of 1375 because we were told to measure, but we also want to interpret. So we want to give that complete sentence where we're saying inside to outside. We do have to be careful here. Divergence theorem, awesome if you have a closed surface, but it's completely useless if we don't have, I don't want to say completely useless, but at first we assume that it's completely useless if we don't have a fully enclosed solid region, because the divergence theorem is designed for a closed surface where we can either do a surface integral over the exterior, or we could do a triple integral over the interior. Well, if your region doesn't have an interior, good luck triple integrating over it. So anyway, what that means is we actually need to know how to compute surface integrals. We actually need to know how to crunch the numbers on one of these things, because we can't always triple integrate. Just like in previous chapters with closed curves, with a closed curve you got to choose between a path integral or a double integral over the interior. But if you had an open curve, your only choice was to do a path integral. Well, in this case, we need to know how to do a surface integral. Anyway, it's not terrible. I know that the formula looks complicated when you look back at the previous slides, because we had field dot outer unit normal dA. Turns out that when we parameterize our surface, when we get a surface in terms of S and T, basically our surface is going to be described as an x of st, a y of st, and a z of st. When you do that parameterization of your surface, this outer unit normal is going to change into just normal of st. Now, we do want to make sure that our normal vectors are pointing out, but this whole unit thing, I'll be pretty honest with you, during this chapter, you don't really need to worry about unit normals so much. We're going to get away with regular normals. If I was in class with you guys today and I had access to the whiteboard, I would show you guys a quick calculation that verifies that the unit normals in the original formula just become regular normals in this parameterized formula. But for now, I would say don't worry too much about it. And if you want me to elaborate, feel free to send me an email, and I can email you a PDF with a quick little write-up of it. But anyway, let's look at this this surface integral here. It's not as bad as you might think, right? You just take your field of x, y, z, and you throw in your parameterization of x of st, y of st, z of st. You dot product that with your normal vector as a function of s and t, and then it just kind of looks like a double integral, right? It's just that this double integral represents what's happening as we move over a surface. These normal vectors here are normal vectors that we're following along a surface. And basically what we're doing is we're accumulating the push of the field vectors in the direction of these normal vectors as we move along our surface. And that'll give us the net flow of that vector field across those normal vectors. But here's the thing that's probably mysterious to you right now. I keep mentioning normal vectors. What normal vectors? We probably should know how to compute the normal vectors for our surface if we're going to do one of these surface integrals. All right, so when we were in the two-dimensional picture, things were nice and easy. We were just using the right-footed normal. Y prime of t comma negative x prime of t, no big deal. When we are in three-dimensional space, we can't just memorize some clean little nice formula like that that's going to give us our outer normals. Three-dimensional space has too many degrees of freedom there, and so the formula for the normal vector is by necessity going to get more complicated. Basically, we have to remember our intuition that comes with being able to compute a cross product. And if we can compute some cross products, we should be able to compute some normal vectors. So this is the one thing where it is much more convenient staying in two-dimensional space compared to three-dimensional space when we're talking our path integrals versus surface integrals. The right-footed normal was, just, you can memorize it. It's easy to work with. Easy to take a dot product with y prime of t comma negative x prime of t, and I'm sorry to say we don't have something that's quite as simple when we move into three-dimensional space. Here's the main idea. If we are parameterizing our surface as some x of st, y of st, and z of st, we could actually find some tangent vectors to our surface by taking some partial derivatives. If I take the partial derivative of that formula with respect to s, that'll be a tangent vector. If we take the partial derivative of this formula with respect to t, that will be another tangent vector. Your intuition for that should be, think back to curves. When you had a curve x of t, y of t, and you wanted a tangent vector, you computed the derivative of that with respect to t, x prime of t, y prime of t. So I think that's pretty natural to you guys right now, that when you want to go from a curve to a tangent vector, you just throw some primes in there, and x prime of t, y prime of t gives you a tangent vector to your curve. Well, in three-dimensional space, we now have not a curve, but a surface. And we can't use primes anymore, right? There's no x prime of st, y prime of st, because what derivative would that prime be referring to? We need partial derivatives. There's two possible derivatives for two possible tangent vectors. Actually, more tangent vectors than that, but two useful tangent vectors at least. The partial derivative of this formula with respect to s, the partial derivative of this formula with respect to y, that's going to be our three-dimensional analog of this two-dimensional example that you guys are used to. Anyway, long story short, we now have two tangent vectors to our surface. I could draw them in. You guys can see them right here. Now, once you have two tangent vectors to your surface at a particular point, you can easily find a normal vector to that surface. All you need to do is take the cross product, right? So there's our x of st, y of st, z of st. Take the partial derivative of that with respect to s. That's what this orange arrow is pointing to right here, this red vector. You do the same thing for this blue one. That's x of st, y of st, z of st. Its partial derivative with respect to t. We've got two tangent vectors. Take their cross product, and you've got your normal vector. All right, so it's not as pretty, it's not as clean as what we were doing in previous chapters, but it works. So you got to take some partial derivatives and then take the cross product of those two vectors, and that's going to give you your normal of st. The nice thing is, when you're working in Mathematica, the computer is going to take care of a lot of this heartache for you, right? Because if you just tell the computer the rule that normal of st is defined as the cross product of these two partial derivatives, it'll just do the legwork for you. When you're doing these by hand, you got to just cross your fingers that the problem you're doing is set up in such a way that taking those partial derivatives and then cross-producting those two vectors is not that painful. And that's pretty much what you should be able to bank on is, yes, these can get ugly, but the really ugly ones are really for the computer. And then when you do it by hand, there's, hopefully the formulas kind of work out fairly nicely. Anyway, guys, once you have that notion of the normal vector, and once we have this idea of computing flow across for both a closed surface and an open surface, we can get some kind of cool little shortcut ideas here. So here's a vector field. This one's not so bad looking. Our vector field is z plus y, comma z minus x, comma x squared. And we've got some surface C that's the bounding surface of the solid region pictured below. There's the region pictured below. Where I'm going to call C the union of this pointy cap C1 and its elliptical base C2. That's underneath, but you can't really see it right now. If you kind of try to turn that thing over, it's got a flat base, and that would be C2. So C is the union of the pointy thing on top and the flat thing on the bottom. Anyway, we're going to try to find the net flow of the vector field across C1. Notice that C1 is not our closed surface, it's the pointy cap. It's the pointy hat. It's an open surface. Anyway, here's the idea. I want to find the flow across this open surface. I can't use the Gauss, the divergence theorem. I wanted to say Gauss-Green, but the divergence theorem. The reason I can't use the divergence theorem is that's a correspondence between a surface integral for a closed surface and a triple integral for the interior of that surface. Well, bad news, C1 doesn't have an interior, it's an open surface. It's a hat that you could literally put on your head. It would look like one of those German hats with, like, from World War I with the spike on top, right? So the C1 is open on the bottom, and so you could put it on your head. It's an open surface. So when you compute the divergence of this vector field, you get 0. Well, that's all well and good, but that doesn't tell you too much about C1 on its own. Now, I do want you guys to be careful about a problem like this. When these sorts of problems pop up in the quiz, here's what I often see students try. They'll think that C1 is a closed surface, and then they will try to invoke the divergence theorem, and then they're going to do something about the triple integral of 0, which equals 0, and then they'll say that the triple integral for C1 is 0. Well, that's not true for the open surface. We cannot invoke the divergence theorem for an open surface. Anyway, here's the trick though. We could try to take advantage of the fact that the divergence of our vector field equals 0, and we are actually able to make a closed surface. It's not the surface we want the flow across for, but we can make a closed surface using C1 and C2. Let me show you C2. All right, so here's a given. Here is the parameterization for C1. This is given information. I came up with this for this problem. You would not have to come up with the parameterization for a pointy hat on your own. I played in Mathematica till I made a surface that I thought looked cool. And I ended up with like a helmet with a pointy top. Anyway, I want to come up with a C2 in order to kind of force a closed surface. And the way I do that is I take my same equation from above, and I'm going to go into my z-coordinate, and I'm going to zero it out. So this z-coordinate is what gives this thing all of its depth. It's what makes it pointy at the top. It's what makes it have this ring around the middle here, and this brim around the bottom. All of the interesting height that you see inside of this hat comes from this z-coordinate. So if I want to make this elliptical base, take the same parameterization from C1, but just throw a 0 in for the z-coordinate, and I've now made kind of an elliptical base. Why am I going through all of this trouble? Well, because now C is a closed surface that you can make by joining together C1 and C2. And once we have that closed surface, we could try to do something with the fact that the divergence of this vector field is equal to 0. Now I'm going to tell you ahead of time, the net flow of the vector field across C1 is not equal to 0. I know that that's the intuition a lot of students have, that the net flow of the vector field across C1 is going to equal 0. It is not going to be 0. The divergence equaling 0 does not mean that there's no flow. It means that, some people will see the divergence equaling 0 and say, okay, this vector field is completely static. It's equal to 0 everywhere, nothing is happening. Well, that's not true. This vector field is interesting. It has lots of stuff happening. Look at this equation. This vector field is not 0, 0, 0. This vector field is inducing flow all over the place. What the divergence equaling 0 tells us is the net flow of our vector field across a closed surface is equal to 0. This problem is not about a closed surface, it's about an open surface. So we are not going to get 0 for our overall answer, but we can do this. Look what I've just done. We know the divergence of this vector field is equal to 0. We know that if we take C1 and join it with C2, we get a closed surface C, and we can invoke the divergence theorem and use that 0 for that closed surface C. So look what I've got here. I've used the divergence theorem here to say that the surface integral over this closed surface C is equal to the triple integral over this closed region, and the triple integral of 0 is equal to 0. So the net flow of this vector field across the closed surface, this pointy hat joined with this elliptical base, that will equal 0. Finally, let's see how to leverage that information. So you guys have seen things like this before. It's a similar trick to things I've shown you before with replacement curves. So in a previous chapter when we did replacement curves, now I'm showing you a trick for a replacement surface. So what I'm going to do is I'm going to take the information from the previous slide. I've written it out like this. 0 equals the triple integral of the divergence, which equals the surface integral of field.outer unit normal for my closed surface. I can break it apart into two pieces like this. This is for the pointy cap. This is for the elliptical base. Now you might be wondering why there's a minus sign right there. I do have an explanation in the slideshow that shows you why. But we've also seen similar tricks before. There was a try-it problem where we were joining two curves to make a closed curve, and we had to reverse one of the curves. It's going to be the same idea here. The reason there's a minus with this C2 is we're going to need to reverse the normal vectors for this bottom base in order to make a region where we have outer normals. So in order to reverse the usual normal vectors, I'm going to have to multiply by -1. The usual normal vectors for this elliptical base are going to point in the same direction as these outer normals here for the pointy hat. If you multiply by -1, or if you put a minus right here into our expression, that's going to correct for us. All right, it was a long time coming, but here's what we finally derived. We know that the surface integral for the pointy hat is equal to the surface integral for that much simpler elliptical base. We have just derived a way of using replacement surfaces. I'm using this 0 combined with this expression, and that's how I'm going to derive that the surface integral for C1, that open surface with the pointy hat, the pointy spike at the top, is going to be the same as the flow across for that open surface that makes the elliptical base of that hat. All right, and then it's a substitute surface, right? It's a replacement surface. C2 is way easier to work with. If you compare the equations back here, I would much rather be working with this elliptical base down here than I would with this entire, metal helmet with the pointy top. Guys, if you want to see the source of that negative sign I was talking about, I've got a visual that goes with it here. When I took C1 and I constructed C2, it's the same surface, just with its z value zeroed out. So the normal vectors are pointing in the same direction. Well, when I want to join these together to make a closed surface with outer normals, I need to reverse these normal vectors for C2 to make my overall surface C. Well, the reversing of those normal vectors comes from, the way we achieve that is by multiplying by -1 there. All right, anyway, let's do the problem. So we can now go ahead and find the net flow of the vector field across C1 by doing the same calculation, but instead for C2. All right, so I have some limits of integration here. Now we haven't looked too closely at this. You might want to see where that ds and that dt, those limits of integration, came from. If you go back to the parameterization that was given information on this first introductory slide here, that was given. So our limits of integration we got for free. So t is going to go from 0 to 2 pi, s is going to go from 0 to pi over 2. So that's how we have our limits of integration. Now, field of x of st, y of st, z of st, that's going to come just from plugging given information for our parameterization into given information for our vector field. So this is just combining two given pieces of information. The normal vector, That one, we have to work for. We don't get that for free necessarily. We have to do some computations at least. All right, so here's our parameterization for our surface C2. It's the elliptical looking base that we have down here for our surface. Okay, so to get this normal vector, I need to take the parameterization for that elliptical base and take the partial derivatives of that parameterization with respect to S, take the partial derivatives for that parameterization with respect to T, and take their cross product. But we have some excellent news here. This z coordinate is 0. So my partial derivatives are going to be pretty nice because our z coordinate is 0. So look at that, 2 zeros in this 3 by 3 determinant. Well, once you throw enough zeros into a 3 by 3 determinant, it basically squishes down to essentially a 2 by 2 determinant in this case. And everything ends up in front of this vector k. Now, I don't want to leave things in ijk form. I also want to do as much simplification as humanly possible. You will notice that we do have the ability to use the Pythagorean identity here, and you will notice that k is the vector that gives us the z component of our vector. So we end up with 0, 0, 2s cosine s. Now, what does this formula represent? That gives us our normal vectors for this flat elliptical surface. And we use it in our formula for computing our surface integral. So we could plug that formula in up top, and now we could take the dot product of field of x of st, y of st, z of st with these normal vectors. And speaking of shortcuts, look at this. When we're taking this dot product, normal of s comma t is 0, 0, 2 sine s cosine s. Well, I have a 0 in this x component, a 0 in this y component. The only thing interesting that's happening in this normal vector is in the z component. So when I take this dot product, the only parts I really care about are the z components of these two vectors. This dot product is going to work out very, very nicely. I could do a little bit of u substitution for my ds integrals. I can use the little power reducing formula for my dt integral. I'm not going to show all the work, but I know that this is something that you guys can practice on your own with a sheet of notebook paper and a couple minutes of extra time, and you too will get 2 pi. I do think that's worth the practice, by the way, because this is the sort of problem you might see on a quiz, right? Maybe the numbers would be a little bit different, the shape might be a little different, but the ideas behind this calculation make a great quiz question. By the way, a common question that I get is, wait, Mr. Grattoni, did you need to reverse these normal vectors in this calculation? Well, not quite. The reversing of the normal vectors was to derive the formula for you for doing a substitute surface. So the reason that I was talking about reversing normal vectors is to show you how, if the divergence of a vector field is equal to 0, and you can make a closed surface out of 2 separate surfaces, the flow across each of those surfaces will be the same. So the reversing of the normal vectors, that was just to show you that this is a technique we're allowed to use. If you have a complicated surface that you don't want to work with, if you can use that surface to come up with a simpler surface that you do want to work with, that the 2 surfaces together make a closed region. The net flow of the vector field across both of these 2 surfaces will be the same as long as your divergence is 0. It's a substitute surface trick. In the actual computation, now that we're actually crunching numbers, there's nothing to reverse. We just take our normal vectors. You just use that regular formula for you take the cross product of your 2 partial derivatives. Keep this normal. Don't keep it normal. That's that pun. Anyway, just keep it as is. You don't need to throw any negatives into it. Anyway, we always want to finish these problems with a little summary here. So the net flow of the vector field across our surface is with the direction of the normal vectors. You could say down to up if you want to. I kind of just prefer saying with the direction of the normal vectors because down and up are fairly relative terms, and especially depending on the surface, down to up might not have that much meaning. But yeah, you always want to, after you finish crunching numbers, you want to interpret that result. Notice that I cannot say things like inside to outside or outside to inside in this case, because our pointy hat is an open surface, and that open surface doesn't have an outside or an inside, right? What else should I mention here? Notice that my conclusion is about C1, the pointy German hat, rather than about C2, the elliptical base. So my calculation was about C2, and I got 2 pi, but I was able to generalize that to information about C1 because of my substitute surface technique. Guys, in general, this is a great technique for triad problems, something that you could see on a quiz as well. So here's the basic idea. If C is a surface that you get by a closed surface that you get by joining together C1 and C2, two open surfaces, and if you're lucky enough to have a vector field whose divergence is 0, then the net flow of the vector field across the open surface C1 is equal to the net flow of the vector field across the surface C2. It's a substitute surface trick. And the basic technique is to trade a crazy surface for a much simpler surface that you are willing to work with. You guys saw this same technique when we were working in two-dimensional space. So we had similar tricks when the divergence of the vector field was equal to 0 for a two-dimensional curve. And we also have a similar idea for when we're working with singularities. So another thing to keep in mind is if you do have singularities in your vector field, if you're lucky enough to have the divergence of the vector field equal to 0, you have the same replacement surface idea that you could do with some closed surfaces there. Here, let me show you. So suppose that the divergence of a vector field, of a particular vector field, is equal to 0. If our surface doesn't contain any singularities, then the surface integral is going to equal 0. If we do have a singularity on the inside, you could use a substitute surface as long as the two surfaces contain the same set of singularities. What I kind of picture is something like this. Let's say you've got a surface C1, and we know that the divergence of our vector field is equal to 0. And let's say we've got an ugly singularity inside of our surface. Well, we can actually replace our complicated surface with a much simpler surface, maybe like a sphere or something, as long as we know that our replacement surface, our closed replacement surface, contains the same singularities as our original surface. And then you guys have seen tricks like this before. If you have multiple singularities inside of your surface, no big deal. Just use a bunch of little spheres to encapsulate the bunch of little singularities. It's the same exact technique that you guys saw in previous chapters. It was circles in the previous chapter, but spheres, circles, they're analogous to each other in two-dimensional versus three-dimensional space, not a big deal. Okay, so I do have some details in Schoology that you guys can see how I did a lot of this problem in Mathematica, but let's look at the pieces that I want you to be able to recognize away from the computer, away from Mathematica. So I do want you guys to be able to look at this vector field and recognize that it does have a singularity at the origin. At 0, 0, 0, this vector field has a singularity. The other thing you should recognize is, even though you wouldn't want to do this by hand, you are very interested in finding out what the divergence of this vector field is. The very first calculation you should do for this sort of problem is compute the divergence of your vector field, and you should be really excited when you see that this divergence is equal to 0. Now you might not be very excited when you see this surface. That would be a pain to parameterize. So finding the net flow of the vector field across this closed surface could get really painful. And a lot of the pain would come from parameterizing the surface, and then even doing a surface integral over that, that surface would get ugly because the normal vector equation is going to be ugly for this, right? These normal vectors are pointing all sorts of different directions, right? Complicated formula for normal vectors. Long story short, I do not want to integrate over this surface. But because the divergence of the vector field is equal to 0, I can replace this weird looking surface with a nice substitute surface, a replacement surface. In this case, I just picked a small sphere. It doesn't really matter how big or how small that sphere is because I only have one singularity in this vector field. And so you could do the unit sphere centered at 0, 0, 0 if you want to. You could do a sphere with a tiny little radius if you want to. It's really a matter of personal taste. I used the computer to crunch the numbers on this. So let me show you how I used Mathematica to finish up this problem for me. So first thing I did was I got a formula for my normal vectors using code that I got from the basics/tutorials. And you guys can see you wouldn't want to do this by hand because this normal vector for the sphere, even for the sphere, even though it's much simpler than the original surface, it's a fairly complicated formula. Now in this case I did set my radius for my sphere to be very small, 0.2. This would have worked with r equals 1. It would have worked for any positive r value. I'm just showing you that typically using a small radius is smart if you are expecting to have, say, multiple singularities. We don't have that in this case, but when you are preparing for multiple singularities, you want small little spheres that are not going to accidentally overlap each other and grab extra singularities by accident. All right, in order for this calculation to work, you need to make sure that you have outer normals. When you use this normal vector formula, there is no guarantee that these vectors are going to be outer normals. When we were in two-dimensional space and we were working with the right-footed normal, what was nice about that is if you had a curve with a counterclockwise parameterization, you were guaranteed that these right-footed normals were going to be pointing out, and that's what we wanted. With this formula, there's a lot more going on here, and when I take this cross product, there is no guarantee that I have outer normals. The only good way to do this is to plot. So I used Mathematica to get a plot of these normal vectors. You can see I just made a table of normal vectors, and I plotted them along with my sphere, and I verified that they are outer normals. If they end up not being outer normals, like if you don't see them plotting at all and you have to turn up the opacity on the sphere or something, it's an easy fix. Just negative normal of ST is a perfectly acceptable way to reverse the direction of your normal vectors. Not necessary in this case, but that's how you would do it. All right, at that point, honestly, you're running it through Mathematica. You know your limits of integration because it's just a sphere, right? And a sphere goes from 0 to pi for s and from 0 to 2 pi for t. Field of x of st, y of st, z of st is just plugging some given information into more given information. The normal vector was computed by Mathematica, and as long as you use n integrate here, you get your result, 19.446. Now that's the net flow of the vector field across your sphere, but it's also the net flow of your vector field across this original surface, which is the one we were actually interested in to start with. We never end with a numerical answer, we always interpret. So here's my interpretation, the net flow of the vector field across this wavy surface. And also, by the way, that replacement sphere is inside to outside. Whew, and we did it. Guys, thank you for your patience. And this is a good stopping point because next we're moving on to surface area. We were going to use some similar techniques, but we're going to get rid of vector fields for tomorrow's lecture. So. Guys, I hope you enjoyed my video. I also have a version that I recorded a couple years ago that I'll also put into Schoology, and you have another perspective on that one. That was a live in-person recording versus this recording on my computer. Please make sure you read the basics and tutorials, Lots of great information in there that you can use on your try it problems. All right, have a great day. Thank you.